Okay, we are going to continue to add to our list of alkyne reactions, and we are up to reaction 9C. If you were very good at your alkene reactions in Unit 5, addition of alkenes, like you're adding halogens or HBr, or you do a halohydrin reaction, if you're good with that, then this is going to be super easy, because it's analogous. We're using the pi bond to add stuff to each carbon. And the first reaction is addition of X2. Now, X2 is just an abbreviation for any dihalide. It could be Br2 or it could be Cl2. Those are the two main ones to use. Reaction 9C, addition of addition of X2. You want to be careful to know what your professor means when they give something like this, Br2. Normally, if you remember from the alkene reactions, we use the chlorinated solvent. Okay. Yes, you want to be careful and really pay attention to your professor whether they want you to think that this is an excess or they really want you to react one equivalent. For every one molecule of alkyne, you have one molecule of Br2. For my class, we're going to try to keep consistent, and when you see a reagent, okay, not the organic molecule, but when you see the reagents, you're going to assume excess. Now, I could change that by putting in front of your 1 mole, MOL, and that would indicate that for every 1 mole of alkyne, you have 1 mole of Br2. Or I could write 2 moles, or I could write excess moles. If I don't write anything, then assume that you have enough Br2 to react all the pi bonds, right? Because you remember that for the alkene, a pi bond would react with Br2 to add Br on both carbons. But we have, where's my hair? We have 2 pi bonds. So actually we're going to add this twice. Put 2 dots on your carbons of the alkyne, because you don't want to lose any carbons, and you're converting it to a single bond. Dot, dot. Okay, and you'll see from the mechanism we're going to do this twice. And yes, it's going to be a tetrahalide. So we did actually add 2 moles of Br2 for every 1 mole of alkyne, and this would be your final product. Okay. Now, again, just a warning, some professors say if I don't put any amount here, you have to assume equal amounts. Okay, for my class, I want you to assume you have enough to react as many pi bonds as you can, so I want you to assume that it has excess amount. Let me show you the mechanism, and this is going to look very familiar, but also a little surprising that this actually works. We have the alkyne, and I'm going to try to stay consistent and draw it linearly. This happens to be an external alkyne or a terminal alkyne. It really doesn't matter. We're going to make that triangle, that 3-membered halonium or bromonium ring. Okay. Let's see. Pi bond attacks, kicks out the Br. Remember the back attack, where you take the lone pair of the initial bromine that was attacked and you actually go back to the more substituted carbon, And that's our first step. And we make that triangle. And it's quite a eyeful, because that double bond actually is still there. I've done this so many times, and I'm still I'm still worried that looks so stupid. If it is, I'm deleting this video. I'll check a couple sources. Br minus. Try to model this. Make a molecular model. It's already hard enough to make a 3-membered ring with all single bonds. Now I have to put a double bond there. I'm trying to visualize this. Let's push forward and I'll double check this, but right now this is my class true. Remember what you attack? You attack the more substituted carbon of the pi bond. Okay, that's because when you have a charge here, you're actually weakening this bond, and actually this bond is even weaker, the one up here, because your resulting carbocation would be more substituted. Okay, don't worry about that. It's the same rule that you used with the alkene chapter, alkene unit. The thing about this is that you still want to do anti-addition. So if they're looking for your professor's looking for the intermediate, this BR, so it doesn't, to me it looks better, just go ahead and draw the BRs opposite in this fashion. Okay. I know it doesn't quite look like that in this case, but it doesn't matter as long as your intermediate has the BRs trans, okay, opposite sides, or anti-addition. We're going to do this again. You're assuming that you have enough reagent to take care of everything that can react. And we'll go down here. Okay, so where am I going to attack next? So this back bond is going to attack the more substituted carbon again. Alright, let's see if we could draw this. The good news is that if you look at our final product, neither of those carbons are chiral. So we would never have to draw wedges and dashes around the tetrahalide part. Tetrahalide. Okay, am I going to do this correctly? Dot. Now, yeah, it actually doesn't. Oh no, I have to do it with the triangle. Okie dokie. BR. 2 lone pairs plus. It doesn't actually matter to me how you draw the other BRs that were already on the chain. And we did kick out a BR minus. And you do have to draw the lone pairs because we're going to use them in the last step. Okay. You still have to attack the more substituted carbon, and this one is because it has no hydrogens. This one has a hydrogen, but also you could say that this carbon is connected to another carbon. This carbon is not. Okay. I know they're connected to each other, but it's not connected to another carbon. Anyway, let's see if that works. Dot. Dot. And now nothing is chiral. It doesn't really matter. Make it look pretty, but it doesn't really matter how you orient the BR as long as you make it look tetrahedral or spread out. That's it. That is addition of X2. This actually might be faster than I had imagined. Before I move on, if you look this up on Google, this reaction, the addition of X2, there are some sources that add a little more ingredients, and we could practice. But also we're going to have to practice ignoring things that aren't really going to affect the product. So once you see the BR2, you're going to do this addition of X2 twice to make the tetrahalide, but there's some helper molecules that speed up the reaction. One of them is acetic acid, and it's typically put in with a salt of bromine. lithium bromide. Don't worry about what these molecules do. Maybe they help with solubility, maybe they help with polarizing bonds, so they're either stronger or weaker, but over years, decades of fine-tuning, chemists have found that adding a little bit of these two helps the process, but it doesn't really affect how you would draw this on an exam. Tetrahalide on those two carbons. Easy. We're going to do HX now. HBr, and we could also do HCl. Do you remember whose rule we used when we were adding HCl and HBr to, why did I do that? HCl and HBr to alkenes? It begins with an M, Russian. We're going to use Markovnikov's rule. Reaction 9D. And this is addition of HX. Okay, that could be HCl or HBr. Let's use a let's use a terminal alkyne, the same one that we did use last time. And again, we'll pick a specific molecule, HBr. No light, no heat, no peroxides, right? Because we'll do anti-Markovnikov. But you'll assume that this is excess. And that helped us last time because we used Br2 twice. We used it here, and we used it again here. So we actually needed more than 1-to-1 ratio. We needed at least a 2-to-1 ratio of Br2 with alkyne. Same thing here. Take a look at this product. Okay, your triple bond turns into a single bond, and your bromines are going to be 2 of them on the same carbon, and that's it. Because we added HBr twice. Where did the other hydrogens go? This carbon at the end has 1 hydrogen. Now it has 3. So we did add 2 hydrogens. Mechanism. And now we're going to have to worry about Markovnikov. Let me remind myself that it is Markovnikov. You can remember Markovnikov with the saying, the rich get richer, and the money is hydrogen. So this carbon has 0 hydrogens. This carbon has 1 hydrogen. The rich get richer. So in our first step in the mechanism, we're going to add the hydrogen to the richer carbon, the N carbon. Ultimately, what you're doing is you're making a stable carbocation and you're adding the bromine on the more substituted carbon. Start from the middle. We're going to get a weird looking carbocation. I understand that we don't see this often. And you know what happens next. The Br minus comes back. And that's our first, well, that's an intermediate, where we've added an H and a Br. Interesting. Because when we add another add another HBr, the arrows should be pretty obvious. What may not be so obvious is that where we're going to put the H and where we're going to put the plus charge. We're still using the rich get richer. This carbon has 0 hydrogens. This carbon has now 2. And now the third hydrogen will go here. So the rich get richer. There's another reason for that, besides following that mnemonic or that trick, this is actually resonance stabilized. Okay, because I'm not going to draw resonance because the mechanism is to get me to the product. But can you see that this bromine lone pair can come down, make a double bond, and make this carbon neutral? And still, bromine and now the new carbon will be satisfying the octet rule. It's just that bromine now would be charged. It would be positive. Let's not draw the resonance. You're going to draw the mechanism and use this carbocation. We did create a Br minus. And so this one's coming in this way. And that should give us the dibromide where the bromines are on the same carbon. Cool. What about this one, internal? Would I ever ask you to draw a mechanism for this? It's possible, but it's going to maybe worry some people because now we can't use Markovnikov rule because both carbons are equally substituted. In that case, you get to choose. You get to choose to put the hydrogen on either carbon because they are equally rich. Okay. In actuality, maybe it's 50-50, but don't worry about that. You just have to worry about drawing the product for something like this. Okay. Now, I mean, you should feel confident drawing the mechanism for this. It's just that you're not using Markovnikov's rule, and the carbocation can go on either carbon after the first step. But if it's just filling the product, oh, good call. Because they're equally substituted, oh man, I didn't see that. And I told you, the carbocation can go on either carbon. Well, where the carbocation goes, the chlorine goes. So there are actually two products. I'm drawing the dots because I tend to, if I don't, make careless errors. And you notice that once the first bromine adds, okay, and we get this, the second bromine has to go on that same carbon because that's where the cation is stabilized by the halide. So it's no coincidence that the chlorines go on the same carbon. But the thing is, they're just as likely to go on this carbon here. You could draw the mechanism to prove it to yourself that yes, you're still following the rule that you're making a carbocation the second time around across the existing halide. Okay. And so these are your two products, and they happen to be not identical. They're different. Okay, so those are two different products. Let me double check because I do have. I want to do some more. Can I introduce anything? Oh, okay. How about this? Off the top of my head. We've gone up to A, B, C, D reactions. Why don't we do one practice synthesis? And I don't want to mess up. How about this? Oh man, I hope I don't mess up. Yeah. That's my target. And give me 1 second, let me think this through. No. This is my target. And the starting material is this. make this from, I should have planned this out better, from the thing is, you're not going to have any clues on the printed exam because they're not going to be dots. But I think you could tell that I'm trying to make up a problem in my mind, and I'm trying to make sure that the dots correspond to where the pi bonds are. Okay. Let me just double check. Okay, there. That's the problem. Or I could write it like this. Here's your star material. I didn't want to draw the dots. Okay, I'll draw it. And then I show a synthesis with a question mark and 3 arrows. It doesn't necessarily mean that there are 3 reactions. It just means that there's more than one reaction that we have to string together. And the final product is this. This is, well, once you do a couple of practice problems, this one is going to seem very easy. Okay, but there's some logic, there's some strategizing to do. The first piece of strategy is that, I think we have an extra carbon here. 1, 2, 3, 4, 5, 6, 7, 8, 9. We have a C9 piece here, C9 molecule, and here we have a C6, 7, 8, 9, 10, C10. Okay, so again, everything in pink and green are going to be my notes and my scratch work and my plan, my strategy. There's an arrow called retrosynthetic arrow, and it's a big arrow that's open-ended, and this means comes from. So it's like a backwards synthesis arrow or backwards reaction arrow. I'm saying that this came from maybe 2 starting materials or simpler starting material. Again, this is just scratch work. A lot of times the professor is not going to grade, your retrosynthetic arrow. And there's a section in the textbook that talks about retrosynthetic analysis. I don't typically do a retrosynthetic analysis all the way to the beginning. I like to do a combination of working forwards and backwards, but ultimately I'm going to have one cohesive synthesis. So in green, my scratch work, I know that I could get a tetrahalide from an alkyne. You just have to draw the correct alkyne. See, here's a green dot and a green dot. So that green dot is here, next to the green dot here, and I know I could get 4 chlorines on this triple bond. But the thing is, where's this methyl group, that one at the end? I have to add that. So see what my strategy is? If I could somehow get to this molecule, I know that I could go to the final product. But I have to get to this now, which I don't have. I don't have that molecule. Okay, so now that was working backwards. Maybe if I work forwards, what can I do with a triple bond? Well, I could add X2, I could add HX, I could do, I'm only trying to use reactions that we've seen. I could do a deprotonation. So if I could deprotonate this, I'll get an anion. Oh, and then I could do what's called alkylation. What am I doing? At the very beginning, I want to do these reactions that I've seen already. Not this one. That's when we make an alkyne from a dihalide. But this one, alkylation. Because when you look at my final product, didn't I add a methyl group? That's an alkyl group. That's an alkyl group. So that's methylation. Methylation. Okay, so at this point in my retrosynthetic analysis, I'm wondering, I gotta add this carbon, and the way I show that is I draw a dotted line. What I'm saying here is that this bond was made. This is a key bond that was made, a key carbon-carbon bond that has to be made. I can imagine that, being a little bit cynical, that this does not seem fun for many of you. But when you have the right tools and when you practice, it's almost like a computer coding, it's like Legos, it's like a puzzle, and then it clicks. Hopefully it clicks. Okay, I'm done with my analysis. I feel like in my head I could piece together the reactions properly without doing a full green arrow, green arrow, green arrow, green arrow, green arrow, all the way back to the start material. The other thing that you want to worry about when you do a synthesis problem for your professor is how do they want you to format it, because some professors have a preference, a stylistic preference. Okay. I say every reaction you do, you got to draw the result. Okay, you don't do reaction 1, 2, 3, 4, 5 and then give me the final product. How do I deprotonate? Use flashcards, right, when you practice. Because hopefully you have a flashcard eventually that has this reaction, the deprotonation. This is reaction 9B. 9B. Okay. Alright. Now, when we went over this reaction, I did do 1 NaMH2, 2 alkyl halide. But for synthesis, you want to draw the product after each reaction. Now, sometimes I'm a little lenient, because if it is a proton transfer, I will allow people to do 1, 2. Okay, but for the sake of showing you every single reaction, I'm going to draw out every intermediate. So I get the anion intermediate. The thing is, how do I make this key carbon-carbon bond? By reacting this anion and doing a substitution. This is an alkyl halide. This is a methyl halide. And if you remember the rules, in the alkylation reaction, you can use very uncrowded halides, a methyl halide or a primary alkyl halide. Again, if this is the first time you're seeing anything like this, then it is going to seem very confusing, like very intimidating. Okay, but the key is understanding these individual reactions, A, B, C, D, so well that then you could pick, I'll use reaction 9A, then I'll use reaction 9D. Heck, I could use reaction 6B, a reaction from a previous unit, okay, when you study the reactions individually. Now I'm running out of room, but I know that I can do tetrahalide formation. Okay, so I use chloroform, but it's a Cl2, and I'm going to add 4 chlorines on those 2 carbons. And that should be my, I'm going to do zigzag, because everything's singly bonded. And I think I just copied the target. Okay. This is a 1, 2, 3 reaction synthesis. And again, I'm flexible. If one of the steps is a proton transfer, which is a proton transfer right here, you could do 1 and then 2 methyl bromide and then skip this middle part. Get to here. And that's how we did it actually when we went over that reaction, 9B. So this is the answer for the synthesis, and again, this is the problem, okay, without any of the notes. How do I make that from this? Okay. Let me just put here retrosynthetic arrow. Some students love doing a full retrosynthesis. I do a combination. I think about what reactions can work at the beginning, and I think about what the last reaction should be. Hopefully I could figure that out, like what intermediate I need for that very, very last reaction. Good. Next video, there's still more reactions. We're going to go over 9E and 9F. Okay, 2 more reactions in the next video.